Hi everyone, and welcome to this video where I am going to run through a few things with you relating the idea of the structures that different chemicals have, the bonding that they have, and the properties that come as a result of them. So this video is going to be a little bit longer than some of the others, so feel free to break it up into chunks or to watch it in smaller parts, but I've just decided to keep everything together in one video just for ease. Okay, so let's start off with something that we should hopefully be quite familiar with. So covalent chemicals, we've met the idea of covalent bonding already, which is where atoms will share pairs of electrons in order to fill their outer shell, and that's what creates these covalent bonds. So the first thing we do when we introduce covalent chemicals is to introduce the idea of molecules and what we would call a molecular structure. The kind of extension to that now, if you like, is that not every substance is actually molecular when it's covalent. The vast majority are, but there are a few examples of chemicals that form a different structure, which is known as a covalent network. So let's have a little look at how that kind of works. So before we go into too much detail looking at the actual structures of them, let's look at the two kind of different ideas of the structures first. So molecules are, as we already know, groups of atoms that are joined together. Now atoms are exceptionally small, they're absolutely tiny, and so molecules are also really small. So if you had some chemical sitting in the palm of your hand, say you had 1 gram of a chemical in the palm of your hands, what you've got in front of you is not just one molecule because they're so small. The only reason you can see them, this 1 gram of this chemical, is because there is billions and billions and billions of molecules all kind of sitting there. Okay, so the reason that you can see something, even though it's tiny, really small, is because there's so many of them. Now, the analogy that I would use when I'm kind of explaining this in class when I'm teaching it is if you imagine a brick, just a normal brick that would be used to build a house. If you imagine sitting that out in the middle of a field and flying overhead on an aeroplane, or going up with a drone or something like that and looking down, you would struggle, probably not be able to see that single brick sitting in the middle of a field. However, if you were to take thousands and thousands and thousands of those bricks and build a building out of it, and then do exactly the same thing, fly overhead or look down using a drone, you would be able to see the building. Not because the bricks have got any bigger, but because there's so many of them together that you can see it. And that's kind of how molecules work. They are tiny, they are individual little things, but when you put lots and lots and lots of them in the same place, there can be so many of them that you can actually see it. A network structure, on the other hand, this other type of structure that we haven't really met yet, is a bit like taking every single one of those molecules and joining them all together to make one giant structure. Okay, we don't call it a molecule anymore, we call it a network, this giant structure where they're all joined together. Now, if you had the same 1 gram of a network substance on the palm of your hand in front of you, you could theoretically have one network. Okay, it's made up of billions and billions and billions and billions of atoms, but they're all joined together to make one structure. So the analogy this time would be, instead of having a house made of hundreds or thousands of bricks, you would have one giant brick the size of a house. If you were to then fly overhead or use a drone and look down, you would still be able to see it, the same as you would the house that's made of the small bricks. So let's kind of try and build on that idea. So if you think about this idea of either something that's made up of small things that kind of work together and accumulate to make something larger. So the bricks to build a house, for example, here we've got a house made out of Lego. Okay, if you were to put that at the other side of your room, for example, you would be able to see it. If you were to put it at the other side of the games hall in school, you would be able to see it. But if you were to take just one of those single Lego bricks and put that at the other side of the games hall, you would probably struggle to be able to pick it out because it would be so small. Imagine then taking a Lego brick and making it so big that it was the same size as the house made of bricks. If you were to put that at the other side of the games hall, you would be able to see it. Now this is quite a good analogy for what we're going to go on to when we look at properties, because if you then imagine how easy it would be to dismantle the house made of many bricks, compared to how easy it would be to smash that single big brick up into tiny pieces. It's obviously going to be a lot easier with lots of small things. And that idea of breaking something down and how easy it is to break down is a nice way for us to try and introduce a couple of the properties that we're going to look at as we go through this video. So I'm a big fan in chemistry of giving you real life examples, things that you can really imagine. So if you imagine water and sand, two things that you should be very familiar with. If you go to the beach, you've seen water and you've seen sand. So imagine just one drop of water, one tiny drop of water. What that contains is the number that you can see on the screen in front of you just now, okay, which is 1.67 times 10 to the 22. Okay, that's a huge number. That many water molecules, roughly speaking, is in one drop of water. Now you can see a drop of water with your naked eye. You couldn't see one water molecule with your naked eye, but you can see this many of them when they're all together. Okay, a bit like the bricks being built together to make a house. It's this idea of being able to see something because there are so many of them. Now the chemical formula, which is H2O, what that tells us is something very deliberate and something very exact when we think about molecules. It tells us that each molecule, okay, there's billions and billions and billions of them, but each one contains 3 atoms. Okay, there are 2 hydrogens and 1 oxygen, and that's what's inside. So this drop of water is made up of lots and lots and lots and lots and lots of water molecules. A network structure, on the other hand, would be sand. So sand in its purest form is a chemical called silicon dioxide, or silica. Now I want you to imagine not having a handful of grains of sand, but imagine just one individual single grain of sand. Absolutely tiny, but you would be able to see it with your naked eye. That individual single grain of sand is actually one covalent network of silicon dioxide. It contains, okay, you can see here it's actually 5 times 10 to the 18. So it contains this many atoms, but what the chemical formula tells us, because there's no molecules, it doesn't tell us what's in the molecule. And we know that 1 grain of sand doesn't contain 1 silicon and 2 oxygens, because it contains this many in total. What this chemical formula tells us is just the ratio. It tells us that for every 1 silicon, there are 2 oxygens. Okay, so rather than having the house made up of thousands and thousands of bricks, like our molecules coming together in water, we have one giant house-sized brick, okay, is the kind of analogy that I'll use, where we have one covalent network, one giant structure with all the atoms joined together to make one big structure, which is a grain of sand. So big, you can see it with the naked eye. So what about ionic compounds? So we've just introduced covalent and the idea that there are 2 different structures for covalent. The good news is that for ionic structures, there's only one. Every ionic structure is basically the same. They have varying shapes, so they can change their shapes, which is something you'll learn about later on in chemistry if you continue to study it. But for National 5 chemistry, all we're really interested in is the idea that they contain they form something called a lattice structure. Now, a lattice structure is a bit like a network. It is one giant 3-dimensional structure where you've got oppositely charged ions. So what we mean by that is that positive and negative ions surround each other. So if you imagine the green being a negative ion, the silver being a positive ion, it's kind of green, silver, green, and then green, silver, green. Okay, green, silver, green, always connected to the one of their opposite charge. Okay, so that's a lattice structure for an ionic compound. Let's look at another real life example. So this is one single grain of salt. Okay, obviously zoomed right in a camera. Again, you would be able to see it on the palm of your hand. If you had a grain of salt stuck to your finger, for example, you would be able to see it. Okay, what you wouldn't be able to see if you look closely is this shape that it forms. It's actually cubic. Okay, so a grain of salt is actually a cube in its shape. And actually that's the reason why it is a cube, is because of the structure of its lattice. This is actually the sodium chloride ionic lattice, and because of the structure being this cube shape, this is why you get the cubic grain of salt. But when you hold 1 grain of salt in your hand, just like 1 grain of sand, what you hold is not billions and billions and billions of sodium chloride molecules. It doesn't form molecules because it's ionic. Ionic forms lattice. And so what you have is one single ionic lattice in one single grain of salt. Okay, now it contains, and again you can see here it's 2.5 times 10 to the 18 ions, okay, with a ratio, again a ratio because we've got one giant structure of every one sodium having one chlorine, okay, which is a chloride ion. So one sodium to one chlorine in a 1-to-1 ratio. But what we're not saying is that it contains one sodium and one chlorine. It's one sodium for every one chlorine. Okay, it's a ratio. So when we're dealing with covalent molecular, all right, we're going to be talking about exact numbers of atoms in a molecule. For covalent networks and ionic lattices, we're talking about a ratio of how many of each are present. So let's start looking at the properties. So what we're really interested in chemistry is how the structure and bonding of these chemicals links directly to the things that we see and the things that we know about these chemicals. So we find these different bonding and structure lead to different properties, which is really helpful for us because if we don't know the bonding and structure of a chemical, we can use what we know about the bonding and structure to test them to identify what type of bonding and structure they have. So firstly, we would want to know, is it covalent or is it ionic? So we identify the bonding. And then what we can do, once we know the bonding, if it's ionic, we know that it's going to be a lattice shape, so that's its structure. But if it's covalent, we want to know, well, is it a covalent molecular or is it a covalent network? And the way we do that is by considering three different properties. We consider the electrical conductivity, so whether or not electricity can pass through the substance. We consider its melting point, that's the temperature at which it changes from being a solid to being a liquid. And we also consider its boiling point, which is the temperature between being a liquid and changing into a gas. And by considering these three properties, okay, we can actually identify by testing whether something is covalent or ionic, and then if it's covalent, whether it will be a network structure or a molecular structure. So this is an experiment that we would do in class. It's a really straightforward experiment actually, using the diagram that you can see on the screen in front of you. What we would do is take compounds that we know to be either covalent or ionic. We would test them as a solid, we would test them when they're dissolved in water, and we would also test them as a liquid by melting them. The results of this experiment are really what we're going to be using, because the results of the experiment are going to be able to tell us a little bit more about the compounds themselves, and we can start to draw some conclusions and start to develop this idea of how to decide what type of bonding or structure a compound has. So remember, the idea here is that we want to be able to test something that we don't know, and so what we do is we start off with things that we do know and we look at the results of that. So here you've got a table of 4 compounds that you would use in class. The covalent ones we use are glucose and sucrose, you can see there. Now they're just types of sugar. So they're nice and easy to get a hold of, nice and easy to handle. They dissolve well in water, all of these kind of things. Sodium chloride is table salt, and copper sulfate is a dark blue crystal solid that you'll have probably seen and actually probably made during your time in chemistry. So what we do is we put them into this circuit with the power pack, with the bulb, put the sample in between, we switch the power pack on and we test whether or not the bulb lights up. The idea is if the bulb switches on, then the chemical conducts electricity. And what we find is the following results. So this first experiment, not the most exciting one to be perfectly honest with you. All the compounds that we test, none of them conduct electricity. So it doesn't really help us, it doesn't really move us any further forward. Remember, we're looking for something that tells us the difference between a covalent and an ionic. So testing them as a solid is not going to help us. So we move on to think about, what if we were to dissolve them in water? So we take the 4 same chemicals, glucose, sodium chloride, sucrose and copper sulfate, we dissolve them into water and then we test them again for their electrical conductivity. So in the same diagram that we drew just a couple of slides ago, we would usually attach two electrodes, which are just long, thin rods made of carbon, and we dip them into the solution of the liquid so that the liquid is between the two wires and is therefore completing the circuit or not completing the circuit if it doesn't conduct. And what we find when we test the four solutions is the following four results. And so now you can see that we have got a difference. We've got something that ionic can do that covalent cannot. And that's a way that we can then test for something that we don't know, whether it's covalent or ionic. We can use that. So what we find is that covalent glucose and sucrose, even when they're dissolved in water, they still don't conduct electricity. Sodium chloride and copper sulfate, which are ionic, do. So they didn't when they were a solid, but they do now conduct electricity as a solution. The last experiment that we do is usually I teach a demonstration because it involves using Bunsen burners and kind of long metal electrodes, and it's obviously going to be quite hot in order to actually melt these chemicals. The four chemicals that we used in the previous one are not quite so straightforward for this one, so we swap to just two chemicals for this one. We use candle wax, which is covalent and obviously nice and easy to melt. You'll be familiar with candle wax melting. And we use an ionic compound called lead bromide that again can be melted just using a Bunsen burner. A lot of the chemicals that are ionic have melting points that are much higher than even the temperature a Bunsen burner can get to, but lead bromides is a bit lower. So when we test the liquids, so we're looking for, again, is there a difference between covalent and ionic? We get the following results. So again, we see a difference. So this is something that we can take advantage of when we're trying to identify an unknown. So let's look at some conclusions. So before we can really draw any conclusions, we kind of just work our way through each type of chemical. So covalent compounds, what we found is that covalent compounds never conduct electricity. It didn't matter whether it was a solid, whether it was a liquid, or whether it was a solution. All of the covalent compounds did not conduct electricity at any point. Our ionic compounds can conduct electricity, and there's a but. They can only do it when liquid, which is when they're melted, or when they're in solution. And that second point that you have on the screen there, this one here, this ionic compounds, this is something that's really crucial, because if I give you a chemical and I say to you, I want you to tell me if it's covalent or ionic, this is the test that we would do. We would either melt it or dissolve it in water. Once we'd done that, we would then look at whether or not that liquid or solution conducted electricity. Remember, none of the solids conducted, it was only the solution and the liquid of the ionics that conducted. Now, to understand why that's happening and to get a little bit of the chemistry behind it, what we need to do is to understand a little bit more about what electricity is. So the first thing to remember is electrical conductivity only helps us with the type of bonding. So remember, we've got two things we want to find out here: the type of bonding, and we also want to know the structure that it has, whether it's molecular, network, or lattice. So to understand a little bit more about why this helps us tell the type of bonding, we've got these two bullet points here. So the first one is that electricity is defined as a flow of charged particles. So we need to understand what electricity is. If you've got anything that's charged, proton, neutron, proton or electron, or a positive or a negative ion, if they can move, that movement of the charged particles is what we call electricity. So let's start with our covalents. Covalent compounds don't contain any ions because they're not ionic, they're covalent. And they also don't contain any other charged particles because they're made up of atoms. And if we go back to earlier in the course, we learned that atoms overall have no charge. So because there's no ions or no charged particles, they cannot conduct electricity because there's nothing charged that can move. So the next step is to then think about ionic compounds. So what we've already met is that ionic compounds can conduct electricity when in a liquid or in a solution. And the question then is why? And it's really simple. This first bullet point that we have on the screen here is a really, really crucial one. It's one that you absolutely need to learn. You absolutely need to know, which is why I've kind of made it bold in capital letters here. is that when we put them into solution or we melt them, this rigid ionic structure, this lattice structure here, is broken down. So the ions are then separated, and what we end up with is this sort of phrase that we're going to learn, which is that the ions are free to move. Now remember, electricity is a flow of charged particles. It's a movement of charged particles. Ions are charged. In a solid, they're rigidly held in place, so they're not free to move. They're held together. They can't flow. But in a liquid or in a solution, they are free to move around. Okay, they're free to move, which means that they are able to conduct electricity. So that's how we can tell the difference between something that is covalent and something that is ionic. Okay, so let's think about melting points and boiling points. To understand melting points and boiling points properly, we need to think back to S1. Something you learned right at the beginning of your time in science was about the kind of makeup and structure of a solid, a liquid and a gas. As you can see on the screen here, solids on the left hand side, very rigid, very organized, everything in nice neat rows and columns, everything close together, almost touching. Okay, the particles that we have here are not able to move around. Particles is the word that was used in S1. So the particles of the chemical are held together, they're close together, they're not able to move, they're very organized. When you move to liquid, we start to get this idea that they're starting to separate out a little bit. The particles are able to move a little bit more. They're able to kind of flow over one another, which gives you that liquid movement that you're used to. With a gas, the particles are even more spread out. You can see they're moving much, much faster, which is kind of shown by this fuzzy sort of shape behind us to try and show the movement of them. So these gas particles are much, much, much faster in moving and much more spread out. So I want you to imagine that this is a solid compound. We can then change it to a liquid compound by heating it up and melting it, making the particles spread out a little bit more, and then into a gas. If we boil it or evaporate it, we can then make the particles spread out even more. And it's that spreading out that's a really crucial idea for going forward. So just to recap here, just to make sure you've got something for your notes, when we melt a chemical, we need to separate out the particles. What we don't do is we don't break the particles. We don't smash up the little circles. We just move the circles further apart. And this idea of particles is fine when you're in S1 chemistry or S1 science, but when we get into S3 and into S4 and we start to learn a little bit more about these topics, the word particle becomes less useful because the type of particle depends on the type of structure. So what we need to do now is to know how that works specifically for something that is molecular, for something that is network, and for something that is an ionic lattice. So let's go through them one at a time, and I'm going to use an analogy that I use when I'm teaching in class to try and help you understand, to give you something as a frame of reference when we're thinking about this. We'll start with molecules. What we need to do with molecules is we literally just need to separate the molecules from each other. Okay, what we're not doing is we're not breaking the molecule. So we're not breaking any of the covalent bonds inside the molecule. So if you think about water, boiling water in the kettle, sorry, you don't break the water apart and make hydrogen and oxygen. Okay, hydrogen and oxygen together is rocket fuel. It's literally the stuff that puts the space shuttle up into the upper atmosphere and into space. You don't produce that when you boil your kettle every time you want a cup of tea. What we do is we take our water molecules and we separate them out from being in the liquid to being further apart from one another into being a gas. Now the analogy that I would use for this is imagine building a house. Okay, we've used this idea before of the house-size brick, or the small bricks together to make a house. So with molecules, we're thinking about the idea of your house. Okay, your house with multiple little bricks. If you wanted to dismantle the house, it wouldn't be easy, but it would be possible. You would be able to sort of chisel apart and break the cement between the bricks and effectively dismantle that house brick by brick if you wanted to. Okay, because you're not breaking the actual bricks themselves, or in the chemistry of this, we're not breaking the actual molecules, it doesn't take an awful lot of effort to do that compared to if you were having to smash the bricks. And when we think about effort, what we're thinking about is energy. And for a melting point and boiling point, what that means is that the covalent molecular Okay, we're separating the molecules. They have a very low melting point, okay, and a very low boiling point. For a network, we go back to thinking about our house-sized brick, one giant brick the size of a house. If you wanted to dismantle that, you would have to actually smash the brick to bits. And that's very difficult to do. It's going to take lots of energy, which is a very high melting point and boiling point. Now in the chemistry, what we're doing is we're taking our large network structure, which remember is one giant structure where all the atoms are held by covalent bonds, and we're actually having to break the covalent bonds in order to make that able to move about a bit more. So if you want to melt something that's a network, you're going to have to put lots of energy in. So we're going to have very, very high melting and boiling points. And that's really useful for us because remember, if we've now decided we've got this unknown chemical, we've tested it, we know that it's covalent because it never conducts. The next question is then, well, is it a covalent molecule or is it a covalent network? So if we look at a covalent molecule like water, for example, all we're having to do is separate out these molecules. Now these molecules are held together by what we would call in chemistry weak forces of attraction or weak forces between the molecules. Not bonds like covalent bonds that are inside the molecule between the hydrogen and the oxygen. They have these weak forces in between. So if we think about that a bit like the cement between the bricks, there's something holding them together, but it's not as strong as the bricks themselves. It's not as strong as the bonds inside. All we have to do in order to boil our water is to separate out those water molecules. So all we're doing is breaking whatever it is that's holding these water molecules together, okay, these weak forces. That doesn't take a lot of energy. You can do it in a kettle, you can do it on your cooker, okay, it's only going to take about 100 degrees C in order for you to be able to do that. So let's compare that to having a look at a covalent network structure. So something like silicon dioxide, which is sand. Okay, in order to melt this, which is quite hard to show in this drawing, but what you're actually having to do is to break some of these bonds that are holding all these atoms together. If you imagine that this structure is quite large, you've got lots and lots and lots of bonds. So if you imagine that in front of you, everything's kind of tightly held together, and therefore it's going to be very difficult for you to kind of manipulate it or move it or make it kind of change shape. If you were to simply break some of the bonds, okay, between these atoms, okay, what you would be able to do then is actually flex it a bit more. It'll have a bit more play, a little bit more movement, and that's exactly what happens with something like sand, which we can melt down, and then if you cool it very quickly it becomes glass. So you might have seen somebody doing glass blowing, which is where they melt the sand down. They have this kind of thick, gloopy, bright red hot liquid. Okay, and it's got a little bit of movement in it. It kind of looks a bit like syrup or treacle in that kind of movement. It's quite slow in moving. And that's because it's still got lots of those bonds present, but some of them have been broken. But that's going to take lots and lots and lots of energy to do, because unlike our water, where all we did was separate out those molecules, which is like chiseling the cement between the bricks, we're now talking about something that's like a house-sized brick, and actually to demolish that, you're going to have to smash the rocks, and that's going to be really, really difficult to do. You're going to have to put lots of energy in, and as soon as you put lots of energy in, you're talking about a high temperature. So that's why we end up with these really high melting points and boiling points. And in this case, it actually ends up being in the thousands of degrees C. Now the last structure, which is actually not as important in this section anyway, for reasons that we'll go through when we kind of sum it all up together, is a lattice. Now the thing that you need to know, and we've already talked about this, is that the ionic lattice is broken down when it is melted or when it's dissolved in water. So when it's melted, we break down the structure, and it works almost exactly the same way as a covalent network. So just like in a covalent network, we have one giant structure with lots and lots of ions held together. So all we have to do now is to separate out those ions. We need to break the ionic bonds. What we find is that generally speaking, ionic bonds are not quite as strong as covalent bonds, and so we have high melting and boiling points, but they're usually not quite as high as our covalent networks. So let's have a look at that in kind of practice. Sodium chloride, which is an ionic lattice, which is table salt. You can see on the left here in our drawing that we've got this kind of rigid structure where everything's remember oppositely charged ions that we've talked about before, where we have positive to negative, and so on. In order for us to melt this chemical, what we have to do is actually separate out the ions and make them able to move. And so what we've got to do is break the attraction between the oppositely charged ions. And as we've learned previously, the attraction between the two oppositely charged ions is their ionic bonds. So we have to break the bonds in order to separate them out. But remember, they're not quite as strong as covalent, and therefore our melting temperature, our melting point, is usually just a little bit lower. So conclusions, let's kind of pull this all together. Unlike electrical conductivity, which helps us tell the difference between types of bonding, melting point and boiling point can't do that. But what it can do is it can help us to tell the difference between the type of structure that it has. Now that's not really that important for ionic, because if it's ionic, it's a lattice. It's as simple as that. So if you do the electrical conductivity on a solution and it conducts electricity, it's ionic. What's its structure? It's a lattice. Simple as that. With covalence though, you've tested it as a solid, doesn't conduct. You've tested it as a solution, doesn't conduct. Okay, so now what we do is we look at its melting point and its boiling point. If it's covalent molecular, okay, which is made of molecules, it's going to have quite a low melting point and boiling point. And if it's a covalent network, it's going to have a very high melting point and boiling point. So we would initially use our electrical conductivity to tell the difference between the bonding, and then our melting point, where we have covalence, can tell us whether it is a network or whether it is molecular. So let's look at that in real life, in a kind of example that you might be asked to do. This is exactly the type of question that you'll often see in a test or in an exam. It's quite often multiple choice, but what we're going to do is we're going to go through each of the four compounds, A, B, C and D, and what I want you to be able to do is to be able to identify whether the bonding in that compound, so in compound A for example, is it a covalent compound or an ionic compound? Once you've decided that, I then want you to figure out what its structure is. So if it's covalent, is it molecular or network? And if it's ionic, then obviously it's lattice. That's the only structure that we have for ionic compounds. So what I'm going to ask you to do now is to pause the video. Okay, have a go at the four, and then once you unpause it, I'll go through the four answers with you. Okay, so let's look at the answers to the four that you've just seen. Compound A, okay, we want to identify its bonding first. So when we're identifying bonding, we are not interested in melting point and boiling point. We're interested in whether or not it conducts electricity, and whether it conducts electricity as a solid or a liquid. Now, what we know is that compounds do not conduct electricity as a solid, but what we know is that ionic compounds do conduct electricity as a liquid. So liquid means it's been melted, it now conducts electricity, therefore A is going to be ionic in its bonding. As soon as it's ionic, it's an ionic lattice. There's no other option for its structure. So if the question was what type of bonding does it have, the answer is ionic. If the question is what type of structure does it have, it is a lattice. And we've not even bothered to look at the melting point and boiling point, because as soon as I know it's ionic, I know it's an ionic lattice. It's as simple as that. For B, not quite so simple. No and no for electrical conductivity. What that tells me is that this compound is covalent. Okay, because the compound is covalent, we now need to look at our melting point and boiling point to decide whether or not this melting point and boiling point tells us that it's covalent made of molecules or covalent network. So we're looking at the size of the numbers. A melting point of 7 degrees C, which is like a cold day outside, and a boiling point of 81 degrees C, which is like a nice hot cup of coffee. So those two temperatures are not very high at all. Okay, in fact, they're really quite low. And because they're low, what that tells us is that it is covalent, and the low temperatures tell us it is molecules. So B is covalent molecular. For C, we start again with the conduction of electricity. What we find is that it doesn't as a solid, it does as a liquid, and therefore not even going to bother looking at the temperatures, it's an ionic lattice. Nice and straightforward. For D, we go back to the scenario of having no and no. Now, because this is no and no, that means that we now need to look at our temperatures. Now look at these two temperatures in comparison especially to B, but actually in comparison to A, B and C. Our melting point is 1713 degrees C. Okay, our boiling point is 2950 degrees C. These temperatures are massive, huge numbers. So because it's not conducting electricity at all, because it's got huge boiling point and huge melting point, that tells me that it's covalent, but it's covalent network. Okay, so that takes you through the kind of process that you need to be able to do in order to identify the bonding and structure in an unknown chemical. So let's recap and pull this all together. There are two types of bonding. So this is the first thing that we learned in this topic. Two types of bonding which are covalent and ionic. In order to tell them apart, we can test for electrical conductivity. That's the only thing that will tell you whether something is ionic or whether it's covalent. Ionic compounds only conduct electricity when in liquid or in solution. Okay, they do not conduct electricity as a solid, and our covalent compounds never conduct electricity. Now, earlier in the topic, we've learned that usually covalent will be only non-metals, and usually ionic will be a metal and a non-metal. And that's a really good rule of thumb, because 99% of the time that's true. But I want you to remember that the only way for you to tell whether something is really covalent or really ionic is to test its electrical conductivity when it's a liquid or a solution. That's the only thing that will tell you truly what type of bonding something has. Okay, we also learned that the reason that our ionic compounds conduct electricity when in liquid or in solution is because their ions are free to move. That's a really important point. That's a question that gets asked an awful lot in a chemistry test or a chemistry exam. Okay, you'll be given some information and asked, why does this chemical not conduct electricity when it's a solid? Because its ions are not free to move. Why does this chemical conduct electricity when it's a solution? Because its ions are free to move. And it's really crucial that we're getting the word ions in there, okay, for our ionic compounds. It's the ions that are free to move. Covalent substances can be either molecules or networks. So moving beyond our type of bonding, we're now thinking about our structure. Okay, to tell them apart, we now need to think about melting points and boiling points. And we really need to be able to explain the reasons why a covalent molecular is lower than a covalent network. And it's to do with whether or not you're having to break the bonds inside or whether you're breaking the bonds between. So between molecules, we have weak forces of attraction that are easy to break, but in a network, we have strong covalent bonds holding it all together, and therefore it's got a high temperature, a lot of energy that's needed in order to break it. Lastly, and this is the nice easy bit, is that ionic compounds, okay, can only form a lattice structure. That's the only structure that they can form. So I hope you found this video useful. As I said at the beginning, it's a little bit longer than some of the other ones that we've made. So feel free to kind of break it down and take it in chunks. But this is a really kind of crucial part of the topic that is really important actually for moving forward. It's one of the most fundamental parts of chemistry, is being able to understand a little bit more detail about bonding and in particular structure within the types of bonding that we have. So take your time, go through the video again a couple of times if you need to. Make sure that you've got these things in your notes. So wherever you see this notes symbol at the top of the slide, that's something that you really need to include in your notes. Okay. And if you have any questions at all or any problems, you can contact your chemistry teacher who'd be happy to go over anything that you've struggled with. Okay, I hope you found it useful and I hope you have a great day.